My name is Vitali Prakapenka, so I'm really excited to start chairing our first session of the workshop entitled NSF-supported GSECARS and compressed DAC programs. We have 5 speakers, and I would like to start by introducing our first speaker. This is Vitali Prakapenka from the University of Chicago, who will share an overview of the DAC program at GSECARS. So Vitali, please, you may start.
Okay, thank you, Stella. So as I have mentioned, we have a pretty good facility in US and worldwide, and they are well adapted to the pandemic, but everyone thinks that has unique facilities, and that is great because we can develop our own with our own vision techniques that's suitable for the many things that you can do at the synchrotrons. So at GSECARS, we mostly focus on earth science, and it is very important because what we can do in terms of probing Earth interior is looking for the seismic response. And to understand the seismic response, we have to know physical and chemical properties of the materials that constitute the Earth and planets. And we are lucky that our most hardest material, diamond, is very transparent and almost entire visible and infrared range. You can see that its transmission started around 200 nanometers and over to the more than 10 micron. And in that case, we can use X-ray, UV, visible infrared photons to probe materials inside the diamond tunnel cell. And the pressure temperature range, as you can see from the plot of the solar planetary system, it's ranged from like 40 GPa to terapascal. And it's very important to probe materials in situ, as even for the very simple material like hydrogen, the phase diagram is quite rich. And to do that, we can use the diamond tunnel cell for the static compression experiment. And it's not very easy to handle materials because it's quite small and require very great alignment and sub-micron level to probe in situ structure and physical properties of the materials. And why it's important, why we cannot use just theory to understand what's going on, why it's we are so hungry to do experiments. Martin Ram and Roald Hoffman, they actually published pretty good papers that give some insight on theory, how they currently understand the physics and chemistry at the high pressure. And they was just trying to check how the electronegativities change with the pressure. And you can see like at 300 GPa, almost all the materials electronegativity change. Of course, it's ideal consideration, but we know that it's true. Everyone who is doing high pressure research knows that at high pressure, like at 100 GPa, we should have a new periodical table. And it's quite true for even higher pressure, like 200, 300 GPa. It will be entirely different world. And in terms of prediction, it works, but it's a way that at some point predict right behavior of the materials, but in reality, we have to conduct experiment to confirm. And often we find predicted properties quite different, very unusual at very different PT conditions. Here are just a few examples of what we have. For example, BCC iron was predicted alloy for a long time ago, but it was observed only in 2007. Transparent dense sodium. So nobody thinks that the metal will be isolator at the pressure, but it was predicted by the theory and confirmed by experiment at different pressure, but still the properties exist. Sodium chloride, everyone knows the NaCl from all the school books, but it has they has different compounds like NaCl3, we can form at about 60 GPa. So, and many others, like compounds that you may not think even exist, like helium and sodium compound, superionic ice, many other things like a new perovskite that was discovered almost 20 years ago. And that basically tells us that the high pressure work is quite interesting, but we have to have right tools. As I already have mentioned, in the diamond tunnel cell, we have sample very small, and we have to combine a few optical axes at submicron level in one point of space. And to do that, we at the GSECARS, we have 3 stations dedicated for the high pressure research. Main is a undulator beamline that we can deliver energy from 5 to 80 kV, and the beam focus down to 3 micron, where you're doing a lot of different X-ray diffraction, scattering, X-ray emission, and combined with different optical spectroscopy. At the BMD station dedicated to study elastic properties of the material, where we combine X-ray diffraction with Brion spectroscopy, and at BMC dedicated for the single crystal diffraction at high pressure, and it's run by PX Square team that Przemek Dera will talk in detail a little bit later today. I would like to mention a few things that was developed at GSECARS, and now it's worldwide used. One of them is a diamond tunnel cell. It's called BX90. Originally, we developed with an indicating counter for Brion spectroscopy to have very large opening, and at the same time, we can put inside the heater and do Brion spectroscopy combined with a single diffraction. But now it's a most popular diamond tunnel cell everywhere and has 2 versions, one is the large, one is the mini, and it's a symmetric design, very stable, and very useful for many studies. And just recently, I will talk a little bit later, we add this mini BX90 to our Cryostat. Another thing that was recognized worldwide is the development of the software. One of them is DAPTAS, that was written by Clemens Sprechen when he was a postdoc at GSECARS. And now it's almost replaced Fit2D everywhere and used not only at synchrotron, but at the lab and X-Files. We keep improving the DAPTAS software, and Eran Greenberg, when he was at GSECARS, wrote a model that allow us to study materials when we are doing 2D map. That's very useful, especially after laser heating, and overplot like a phase position on the sample image. So we can, after mapping, can immediately see distribution of the phase after laser heating, after phase transition. So it's very useful to have. A few words about what the technique we have. It's an optical schematic for diamond tunnel cell design at IDD. I will not go in details. I would just say that we are using coaxial laser heating with X-ray beam with a carbon mirror that focus both laser and X-ray on the sample. And we are using flat top laser heating to improve temperature distribution and reduce temperature gradient. Everything is controlled by Apex window. Considering that the experimented high pressure and temperature quite difficult, and we constantly have young scientists, students, we have developed some routine that allows users to do it very easy. What you need to do is just to set exposure for the temperature, for detector, laser power, and then you just, on this window, you press a button, burst, and software will calculate how many temperatures you need to measure within X-ray detector window, and how long laser should be on. So after measurements is done, type task is loading diffraction, showing what the phase you synthesize, showing the temperature distribution, and within the heating time, and also update the log file, and even collect your quench room temperature sample. So there are no user interaction. And actually this technique helped us a lot during the pandemic, when we have a remote operation, when the connection is not very stable. With this technique, Jeff, who was a graduate student working with APS-U, was be able to do quite difficult experiment on melting. You can see the diffraction pattern and rising the background, showing that the sample is molten. So he subtracted and plot versus integral versus the temperature, and you can see where is the solidus and liquidus. And actually he mapped quite a bit phase diagram of iron carbon system that actually help us better understand composition and within the iron carbon system in application to the earth and molten core. Another example from the melting to the single crystal that Stella did is to study material and try to understand what the structure of especially low symmetry material at high pressure. And what if you compress MgCO3 to high pressure, almost 100 GPa, you can see that the sample reflection are quite large and diffuse scattering, and it cannot be used for structure determination. If you integrate as a powder, you will never figure out what the structure is. But after laser heating and careful quenching, you can see you can synthesize quite good spots, and that can be used for structure reduction. And what she did, rotated the diamond cell plus minus, I think, like almost 38 degree. Yeah, it's a total, so 75 degree, 1 second per half step. So total, we have 150 seconds time, and collecting images at each step. And she was be able to treat the selecting one of the grain and treat as a single crystal and solve the structure, long time, 15 years old mystery of the MgCO3 two structures. Even more, when we have significant change in composition, what we can do. And actually, Elena Bykova was be able to study iron oxide at high pressure, that particular one at 80 GPa, and you can see two samples. And here is a zoom of them. They're quite small, only about like 10, 20 micron in size. But actually, after laser heating, what we found is a mixture of different phase. And there are no ways that you can figure out what's going on without a single crystal approach. As you can see, each pixel here is correspond to the one data set for a single crystal. And she was be able to map different phases depend on the heating conditions, and driving back heating and temperature gradient, you can estimate what their composition could be within the mantle, Earth's mantle. And the main conclusions that the iron 203, iron 304 may decompose at the condition of the Earth's lower mantle and play a significant role in oxygen cycling between Earth's reservoirs. So it was published in Nature Communication. What's happened if we don't have any diffraction, so like amorphous non-crystalline materials. And we are always looking for new developments that others have, and this particular one, solar slit, multi-channel collimator, that was developed at SRF, and we use it to apply not only for the Paris-Edinburgh cell that was designed for, but for the diamond cell. As you can see, this is absorption. This is a scattering from the air is the black, and this is a Compton scattering from the diamond without the samples. You can see it's a huge, and to reduce that background, we can use a number of slits to collimate a scattering from the sample. And here is an example of without solar slit. Dash is a background and green is a sample. And when you subtract, you have very noisy pattern. But when we are using a solar slit, we have significantly improve signal to noise ratio. And here is our setup, how it looks like. So we have a diamond cell, we have a laser heating system in, solar slit, and Pilatus detector. And we found that this Pilatus detector fit well exactly the size of the solar slit. And with this system, Clement's pressure was be able to reach 170 GPa starting SiO2 glass. And you can see that the structure factor quality of the data is quite good for a relatively low Z material compound. So we can get up to 10 Q. And for this Q, we was be able to get better distribution function and versus the pressure. And you can see that the coordination number calculated for SiO2 is increasing at around, starting around 10 GPa. At 4 GPa, it starts to get to plateau, but it still keep rising. And actually, we were surprised that it's not staying at 6 that it was expected, but it's going up. So approaching like 7 coordination number. And you can see that it's pretty reasonable in terms of oxygen packing fraction. As you can see, it's for the ideal iron 2 type that it's predicted for SiO2, the coordination should be around 8. We combine, as I mentioned, with the laser heating. As you can see here, it's very tight, and actually the distance between the solar slit and the mirror, I think it's around like 200 micron. And to check if it's not touching, I actually just put the paper to see if it's paper can go in or not, because you cannot see by eye. So we collected quite a bit of data, and actually it's available for users, and few papers are under the review right now. You can see that what we collected, red is a diffuse scattering from the molten material, and blue is a quench. You can see the image that clearly showing polycrystalline pattern before heating, and during the heating it disappeared, and you can see diffuse scattering. So it's very great technique to study melting structure of the melting materials or fluids at high pressure, especially for at a relatively low Z. Just like in the beginning, I mentioned that we have a unique technique at GSECARS, and it's mainly because of the combination of what we have. And on the example of H2O, I can show you how we are dealing, studying these materials by different technique. And you know that it's very important to this material, not only for life, for our everyday life, but also for the Earth's interior. And so the I7 inclusion in diamond was actually discovered in the diamond as an inclusion. And for this technique, Oliver suggested for us to study, we use combination of X-ray macro probe and diffraction technique. So even if it's not diamond Anvil cell, but our technique, it's very ideal to study inclusion, because we can see very clear where is the sample, where is the inclusion. We can correct on the depth to keep it on the rotation center. Scanning with the exhaust, we can find where is the inclusion located. And as a result, was be able to get diffraction from the I7 at that was particular in this case at 8 GPa in the within the diamond. And that basically first time when we observed I7 as a natural form, not artificially synthesized, and it was accepted by International Mineralogical Association. The same way bridgemanite was discovered a few years before. So you can see that the ice is in the mantle, and it's very important to study H2O at much higher pressure and high temperature. But what about elastic properties? Here, Bin Chen from University of Hawaii suggests to use Brion spectroscopy to analyze elastic behavior. But it's whoever deal with the ice knows that it's very difficult to synthesize single crystal material, but Bin was be able to synthesize single crystal at above 10 GPa after transition 6 and 7 of ice. And at the end, we have a crystal orientation, probe with X-ray diffraction, and also measure it with Brion spectroscopy elastic moduli. And he found that the elastic anisotropy has a few jump at around 10 GPa and around 20 GPa. So the far highest pressure point at around 70 GPa. Another interesting stuff was predicted for a long time is a superionic state of the ice. And for many years, it was only prediction. Just recently, it was a few papers from the shockwaves experiment. And what we did, actually, it published in 2013. We actually start to work on this ice even a couple of years early. What we did, we used quite unique system. We used porous carbon that was filled with water. And in that case, we can heat the water with a laser uniformly and test the structure and see what the phase transition appeared. So what is a superionic state? It's when we have solid oxygen lattice, whereas the hydrogen, it's kind of like, you can consider a molten, it's flying around. So it's like molten hydrogen within BCC, FCC lattice of oxygen lattice. So what we did, here is one of the example laser heating experiment for ice. So you can see the black is the tissue ice that we use as a insulator, and you can see gold as a pressure standard and absorber at some experiment, and also ice 7 blue. When we increase temperature to 1500 degrees, it just narrow and reduce the stress. But at about 1600, we can see new peaks appear with the BCC phase. So the density reduce abruptly. So, and when we increase temperature higher, we can see new peaks appear that actually tell us that we have an FCC phase. And when we quench sample, we back to I7. So there are no any chemical reactions. So it's just pure phase transition. When we go to higher pressure, we can see formation only FCC phase. So at 150 GPa, black is the I7. When we heat it up, you can see appearance of the new peak that belong to FCC lattice. When we plot all our data, you can see that actually I7 ice phase diagram even more complicated than was believed. Now we think that we have 20 phases that already was recorded for H2O. You can see the BCC phase is like in very narrow pressure range, and then we have mostly FCC that actually extend to very high pressure. And if you compare to the theoretical calculation, the prediction was that transition will be around 100 something GPa. And from some other data from Roser, we can see they saw some phase transition, but not clear what was happening there. So our data now explain many unpublished data with unknown phase. The paper is accepted in Nature Physics and will be published soon, I think within a couple of weeks, where we discuss more about application to the planetary for ice giant and compare with the shockwave data that also available. Actually, here are some of the points, and they are slightly different from what we observed in static compression. If you want to go to much higher, temperatures, we are using pulse laser heating that we combine storage ring structure with pulse laser and detector gating mode. So you can see the pulse of the laser and the window for the detector and the temperature measurements. We can easily go to high temperature, and it's useful because we can reach the temperature that we cannot do with a normal continuous wave heating. You can see that we have, for this particular sample in continuous mode, we cannot go to even 1000 degrees, but with the pulse heating, we can go to 4000, and you can see a new phase was identified, and the run is working right now on this manuscript.
One more minute.
1 minute, okay. Okay, I will skip their superconductivity that actually help us also with nice technique to help solve the structure that we need, structure that was responsible for the superconductivity. We are pushing limits to the very high pressure experiment to above terapascal in collaboration with Dubrovinskaya and Leonid Dubrovinsky. They initiated project to reach very high pressure and was be able to reach 1 terapascal. It's the highest pressure ever recorded for the static compression, and it stimulates actually developments of toroid type of the diamond Anvil cells that routinely can go to 600 GPa. And also for the high temperature X-ray emission spectroscopy, we can do it not only often, but in combination with a new detector, whereas we can scan only analyzer, but keep detector steady, and combined with the laser heating, we can study the spin state of the iron. The new systems that we have are actually not only X-ray, we develop optical system. One of them is Raman system. It has 5 laser line, and actually it's very nice and robust system. It works very well up to 10 reverse centimeters close to the laser line, and we can study materials also in remote mode. So it's control everything by APEX. Just recently, we have commissioning the Cryostat that allow us to do double-side laser heating when we have sample cooled down to nitrogen temperature. You can see the temperature is below 18 degrees, and we can still do the laser heating. So here is the transition ICE7, and it start to split, transforming to ICE8. And actually, at the same time, we can heat it up and measure diffuse scattering from the molten materials, and the temperature jump because of the superionic phase transitions that I mentioned before. And one of the recent things that we did was dynamic compression. It's the first time we did a GSECARS. It was initiated by Sylvia and Arianna and Wendy. And you can see, hopefully you have good connections, that when it start compression, the reflection change. At this time, it was not very fast, only 10 to 100 GPa per second, but we are working to get much higher speed, and definitely will benefit from the MBA upgrade. Mark Rivers will talk a little bit later about detail about APS upgrade, but the main thing that it will happen on April 17 in 2 years, on 2023. And what right now we have electron beam profile, which will convert to the spot size, and it basically increase. We can have more flux, hopefully 10-100 times more in focus beam. We can go down to 100-300 nanometers. That is natural requirements for the sophisticated DAC experiment.
There's a lot of questions, so please finish up.
Yeah, we'll finish. And so it's very important that we have new developments with the APS-U, and your input will be very precious. And one of the techniques that I want to discuss with you is a coherent X-ray technique. You probably want to consider coherent X-ray diffraction imaging, a photon correlation spectroscopy, where you can get the sample size diffusion. So it's very interesting technique, and we hopefully can have it at after APS-U. But we need your input to know if we need to develop it or not. And I will leave you with this slide telling that we are doing pretty great. Thank you.
Thank you, Vitali. That was a great talk. So we already have some questions. We can only do some of them. So Sergey Lobanov, could you please unmute yourself and ask your question?
Sure. Hi, Vitali. Could you please tell us about what do you think about non-gray body temperature measurements in laser-heated diamond Anvil cells?
It's a good question, and I know that you're working on it, but considering many things, temperature measurements that we have is basically we feed the gray body radiation and changing emissivity and fitting emissivity. Of course, there could be some effect of the sample if there are absorption, self-absorption of the sample. But when we are using transmitted insulating layer of pressure medium, then the error bar is a minimum. But yeah, it's an important question and need to be investigated.
Thank you.
Thank you. Alexandra Tamarius, could you please unmute yourself and ask your question?
Yeah, good morning. I'm not sure why my camera's not working, but hi. My question was about, you talked about, there we go, talked about record-breaking pressures.
Mm-hmm.
And one thing that I don't have a good understanding of yet is the difference between a beveled toroidal and a secondary anvil. Just kind of
it's a
quickly, what's the advantages?
Advantage is a stress distribution on the diamond. So what we want to have is a reduced stress that when we transmit from the highest pressure point to the almost ambient pressure point. And all this technique, double stage anvils, that is nano crystallite diamond, help to keep their stress at the minimum. And toroid type, it's known for a long time that toroid shape help to reduce stress when we compress the sample. Yeah, so basically is reducing the stress on the diamond and keep it still alive, not to break it.
And then which one's the best out of those three? I was just curious.
The best, the ones that it works for you.
Okay, all right, thank you.
That's great. So we do have a few more questions, some also in the chat, but in interest of time, maybe we should just move on. So please type your questions in the chat and the speakers can address those there.